Good afternoon. My name is Dwayne Davis, and I'm one of the faculty members here at SciTech. And it is my great pleasure to welcome you to our SciTech lecture for this afternoon. A few years back, there was a group of us who were huddled over coffee, and the idea of these lectures came up. And it seems like it was only yesterday that we did that. But since that time, we've had 50 of these presentations, so this is number 51. We've had roughly 3,300 people who have attended face-to-face with these meetings. And in addition, we have recorded and or streamed material away from here, so there's no telling the influence we've had in other spots. But we're so happy to have you here today, and we know that you're going to enjoy this lecture. And I'm going to turn it over to our introduction speaker.
Thank you, Dwayne. I'm Scott Sewell. I'm the Vice President for Technology Acquisition and Development for Cook Medical. I'd like to thank Russ Reed for inviting me today, and Russ insisting that I wear a tie, so I brought my tie. But actually, Russ contacted me the other day and said, would you introduce Mike Battaglia? And I said, wow, that would be a great honor. So I'm actually honored to be here today to introduce Dr. Battaglia. Dr. Battaglia is a serial entrepreneur, an expert in academic technology transfer, commercialization. Now, I know that for a fact because I used to correspond with Mike a little bit over at Wake Forest in our separate roles, but working with Mike's tech transfer office. So I can vouch that Mike is an expert. So that's true. He's co-founder of Wide Eye 3D, which develops 3D printing solutions for mass manufacturing, and the CSO for Arctic Incorporated, which commercializes technologies to modify the weather for agricultural applications. My lawn's still pretty bad, so I'm still waiting for you guys. Dr. Battaglia has over 16 years of experience in academic technology transfer. Do you guys know what that is? So it's basically when places like Wake Forest, where physicians or scientists come up with ideas that might be helpful to patients, in that case. They would then bring to Mike's office. He would see if there's any intellectual property, see if there's any commercialization possibilities, and then Mike would do the outreach to other companies like Cook and other companies across the country to see whether they'd be interested in bringing the product to market to help patients. So it's a very necessary role, and it really does help patients. Mike served 12 years at Wake Forest University as Executive Director of Commercialization and 4 years at North Carolina State University as Associate Director, then Director of Technology Transfer. In addition, Dr. Battaglia has been active regionally and internationally to support in the support of technology transfer and biotechnology. And actually, Russ and I have, for many years, have worked with Mike in those types of organizations. And he was and continues to be a leader. He has served on the boards of the Association for University of Technology Managers, the North Carolina Biotechnology Center, the Biotechnology Advisory Council of the Piedmont Triad, and the North Carolina Center for Innovation and Nanobiotechnology. Dr. Battaglia received his PhD in biochemistry from the University of Texas at Austin and his BA in chemistry from the University of Chicago. He's a certified licensing professional with the Licensing Executive Society. So I'm, again, privileged to introduce Mike, and let's welcome Dr. Battaglia.
Well, thank you all for coming. It's warm out there, let me just say. So today, I'm normally giving speeches about other people's technologies, what's going on in the university, the new inventions that are aligned with industry. But today, I'm going to tell you a little bit more about me. And the title of the talk is Adventures in Innovation from the Bench to the Stratosphere, and you'll see why in just a little bit. So as I said, I want to talk about me. I spend a lot of time talking about other people's technologies, but I think it's important to share my experiences, my personal experiences, so that you can relate to who I am. A lot of you know me, but I think some of you are going to see a different side of me and some of the things that I like to do and that really get me going. So Scott talked a little bit about my background, but as my best friend Bruce Ekholm told me in college, or I guess just after college, he had moved to Seattle and I had moved to Texas. And he said, out here in Seattle, it's not what you do during the day. No one cares about that. They want to know what you do on the weekend. All right, so on the weekends, my passion happened to be around aviation. In particular, I fly gliders and powered aircraft, but I fly gliders more often than powered. I am a scuba diver, but don't do that quite as much these days, but have been sharing it a little bit with my younger son, mountain climbing, and I'm also a licensed skydiver. So, I guess with this, I like to take some calculated risks in my life because the payoff often outweighs the challenge. As Scott mentioned, my background is in science and commercialization. So after I finished my PhD, I actually did several years of postdoctoral fellowship at UNC Chapel Hill at the Lineberger Comprehensive Cancer Center in the Department of Chemistry. I worked a lot on molecular immunology and structural work. But I soon found myself needing to, we were just, as a family, decided we're going to stay in North Carolina, and I needed to find a job. So that's how I found my way into tech transfer and got my first job at NC State and quickly learned through a lot of mentorship and a lot of on-the-job training how to start companies, do license agreements, manage intellectual property, all these things that I had a little bit of intellectual property coursework at UT Austin, but outside of that, knew nothing of this field. And over 16 plus years in the field, I've helped to launch a number of companies around the state and license technologies out of the university. So BioResource International out of NC State, they make food additives for the poultry industry. Biomark Pharmaceuticals, Cree, I helped settle some litigation and put a big license in place early in their career. If you're not familiar with Cree, they're the ones who brought you blue light lasers. And with blue light lasers, the ability to store vast quantities of information on CD-ROMs and in the cloud. Dow AgriSciences for plant biotech, Pfizer for pharmaceuticals. Scott mentioned the Association of University Technology Managers is an international society dedicated to promoting the field of technology commercialization. And I've served on the board a couple times as vice president. Kachera Pharma that Russ and I have worked on here at Wake. It's not always bioscience. I helped spin out the predictive assessment of reading, which is an early childhood assessment program out of Wake Forest. Carinetics, which some of you are going to be familiar with, maybe one of the more successful biotechs in town that spun out of the Institute for Regenerative Medicine in Wake Forest. But today, after 2.5 years outside of the university, I do some consulting in that field, but now I spend more of my time devoted to promoting the development of 3D printing technologies and assisting companies and some university researchers to transition their ideas from classical manufacturing to 3D printed products. Just a shot of what some of this looks like. I'll just say that in this, there's so many things coming at us in this day and age. Some of it passes under people's radar. 3D printing is going to be one of these technologies that in 10 years we're going to go, what happened? We are just now at the stage where 3D printers look a lot like the early days of the personal computer. A lot of people don't know what they're good for. Why would I have one in my home? How is this going to be relevant? Do I really need more than 8K? But what we don't realize is the power of the technology will disrupt everything from manufacturing through logistics and even currency, because no longer will you have to manufacture something in Winston-Salem and ship it to China. You can merely port the files over the internet and have something made on site. And there are a couple companies that I'm singling out here. Carbon 3D has developed a very unique 3D printer platform which does real-time polymerization. And those parts, that plastic part, which is coming off a printer, is indistinguishable from injection molded component. So think about that. You know, the tool and die that goes into, maybe people don't appreciate, but the machinery that goes into forming a piece of plastic into a part can now be printed on a machine, and the physical properties are no different between the two. It allows for mass customization. It allows for product opportunities on the scale of one, whereas injection molding takes months and literally tens to $100,000 just to get set up. XJet is doing something similar, but in metal. And so with this comes a lot of opportunity to disrupt processes. The engineering cycle can go from weeks to months down to hours. This is a project that we did about a year ago, manufacturing a medical simulation of an eye and an eyelid so that surgeons and technicians could practice their technique before they actually practice on a person. And we brought in an expert in the procedure to cycle through what it would take to modify the product, modify the components, produce it, test it, and then go back to the beginning, so that within a weekend we went through multiple cycles of design and build to come down to a final product to go with. And then, you know, Wide Eye Technologies as a company takes advantage of that. We can scale, and we can use that design process to go to manufacturing. And I think that's the real secret here. 3D printing is not it's not a new thing, but it's absolutely disruptive. And the next phase is going beyond the prototyping to the actual manufacturing of components. So that's a bit about who I am, where I've come from over the last 16, 18 years of my career. But I'm going to shift gears to tell you a bit about a big project in my life that I do on the side called the Perlin Project. And the Perlin Project, I'll get into some of the history through some of these slides. The Perlin Project has built a near-space sailplane. And I've been involved with the Perlin Project for about 9 years. So I've been doing this in my spare time, weekends, after hours, vacation, for almost a decade. And we have some really exciting news to tell you about this project and what we've done and where we're going. So the Perlin Project is a nonprofit organization. We set it up as a 501c3 charitable organization with the focus to develop this near-space sailplane. And unlike many programs out there in aerospace, we are an all-volunteer group with people from a number of countries, North America, South America, Australia, Europe, all dedicated to the design, the build, and the flight of this platform. And we have a number of goals that we've set out to underpin this project. Obviously, the aeronautical exploration is a big component. We want to see how high we can go. You know, a lot of people out there in this new space era are pushing the limits of what's possible in terms of speed and altitude and orbit. And we are pushing the frontiers of aviation to take a motorless aircraft into the stratosphere. And some of the reasons behind that are, we want to understand what flight regimes would look like at those altitudes, partly because that aerodynamic advancement will allow us to potentially understand efficiencies in flight. I mean, everyone wants to save fuel. Airlines live on the margin between their fuel costs and operating costs and profit. So any savings that can be had by flying higher and cleaner and more efficiently will lead to the bottom line. In addition, the stratosphere on Earth simulates the atmosphere near the surface of Mars. So if we want to learn how to send probes across the Martian landscape through the Martian atmosphere, we can fly in our stratosphere and learn a lot about how that will impact the things we design that go to Mars. In addition, we have quite a bit of interest in meteorology. We have a meteorologist, our chief meteorologist, who's been with the project since really the late 90s, Elizabeth Austin. Leads that. She is now a fellow of the American Meteorological Association and an expert in wave, and we'll talk a little bit about wave in a few minutes. But there's a lot to understand about the stratosphere and the mixing of our atmosphere. A lot of chemistry goes on in the upper atmosphere because of the cosmic rays and the particles generated, the UV radiation. That milieu creates an environment that we're not completely clear about. NASA terms the stratosphere and the mesosphere as the ignorosphere. It's that part of our atmosphere that we go through in a rocket, or the balloons go to the top of, get over. We are looking to sample and explore that in more detail to understand how it impacts global weather. And then finally, we have a big STEM education mission. We have a number of schools participating with us who have built experiments and who are flying those on our aircraft. And this just gives you a snapshot of the team. The team this slide is probably 6 or 7 years old. The team has changed over time. We've added more people. As I said, I started this when it was just an idea. So before I can go into the more detail about the aircraft and what we're doing today, I want to talk a little bit about the basics of mountain wave soaring and how we can use the atmosphere to our advantage. So you have to keep in mind this aircraft has no engine. We're looking to go to 100,000 plus feet with no aircraft engine, no rocket, no propulsion of any kind, other than the energy in the atmosphere itself. And there are several ways that you can get an aircraft flying without an engine. Now, an aircraft doesn't need an engine to fly. By definition, the wing itself creates lift and can go through the air. Sustaining that lift is really what you need the engine for. We can get around that using the energy of the atmosphere. And so there are three major types of lift I like to talk about. There's thermal lift, and it's predominantly the energy that we see in the atmosphere around Winston-Salem. It's where the sun differentially heats, the ground, and the darker patches create hotter air than the surrounding air. And that hot air creates a bubble, and that bubble of air rises in what's called a thermal. And at the top of that, like you'll see outside today, are big puffy clouds. It's the froth on the top of your cappuccino. And we can ride that parcel of warm rising air up into the atmosphere and stay aloft and go cross country and fly around. It's not uncommon to fly literally hundreds and hundreds of miles and stay at thousands of feet in the air all day long. I mean, I've been up many times over 5 hours and came down because I had to go take a shower because I had to go out that night. So there's a lot of energy in the atmosphere, and we can take advantage of it. Now, there are a couple other types of, we don't use that to go to the stratosphere. That's good for getting around the state and making cross-country trips, but it doesn't take you very high. Usually it peaks out at the cumulus clouds, puffy clouds in the sky. Another type of lift is ridge lift. It's where the winds are blowing up against a feature on the surface of the Earth, and that upwelling of air creates a lift along the line of the ridge, so in and out of the slide, and you can fly along that feature back and forth. Also great to go long distances, but normally you're flying about 50 feet off the treetops. Can be a little dicey depending on whether you can land out or not. Again, we don't use this type of lift either. This is, again, useful for going cross-country, and it's a big rush to fly this way. The way that we are getting to the stratosphere is utilizing the third type of lift, wave. And wave is lift that's generated on the leeward side or the downwind side of a feature on the surface of the Earth, like a mountain. Doesn't have to be a mountain, but it's often a mountain. And like giant boulders in a river, mountains create standing waves. If the conditions are correct, will create standing waves downstream of that feature, much like you'd see in a river. So if you go to the Yadkin and you take a look for a big rock in the middle of the river, if you notice, pay attention, just downstream of that big rock, you'll often see standing waves. They don't move. The river continues to move on downstream, but in that area just downstream from the rock, you see peaks and valleys. You see the froth of the peaks, and you see the dips and the valleys of the water. Same thing happens in the atmosphere. It's just a different kind of fluid. And again, if the conditions are correct, we can, and by that I mean if the winds aloft increase with altitude and the atmosphere is relatively stable, you will get these this wave train that is on the downwind side of the mountain range. And that's just depicted here. And these clouds that you'll see, and I'll show some other pictures, are called lenticulars. They don't move, unlike a lot of clouds that we'll see. And if you go outside now and look at those cumulus clouds, they move with the atmosphere. They're moving with the winds aloft. But if you look at these types of lenticular clouds, they are they sit in position just on the other side of the mountain range, and they don't move. So this is a really good picture from out west. I'm going to talk a little bit about how people learn to fly in this in just a minute. But this is around the area of the Owens Valley, which runs from northern California, Nevada, south to southern Nevada and southern California. It's a long rift valley, and you have the Sierra Mountain Range on the western side of it. And at about this time of year, with the westerly winds, you will see these kinds of cloud formations forming. Now, in the United States, there's some cap to how high you can go. We'll talk about that. But these clouds will go up 40, 50,000 feet. So we're talking, well to the top of our troposphere. I'll back up for just a second to say, for those who are not familiar with the atmosphere, I'll talk about two major components. I've talked about the stratosphere, and I'm going to talk about the troposphere. We live in the troposphere, so it's the air we breathe. It's all around us. It goes up about 10 kilometers, and then we get to a place called the tropopause. And from there, we go into the stratosphere. And so those are the three components I'm going to be talking about. It was discovered by accident, really, in the 30s that you could fly in this kind of lift. People had experienced a lot of turbulence. And I will say, back up here a second, right down here, you'll see that you get the standing wave. But also, if you look in the river, just on the downstream side of the rock, you'll see a lot of turbulence. And I've done a lot of whitewater kayaking. Sometimes if you get trapped in that, you'll get trapped in that. It's very turbulent. We call that the rotor. In the other way. In the 30s, in Germany, people experienced a lot of turbulence, but they typically got out of it. And keep in mind, this is only 35 years after flight was really being started to be explored. So this was real exploration. A guy named Jakob Kuttner fought his way through some of this turbulence to discover that there was wave available, and flew an open cockpit aircraft to over 22,000 feet. There were some other attempts and some other records kind of early in those early 30s and 40s, but the mecca of wave soaring quickly moved to this Owens Valley in the western United States. As I said, these are the Sierra Nevada mountain range. The valley is on the eastern side, and it runs from northern Nevada to southern Nevada, northern California to southern California. It has a very nice configuration because you want those winds to be perpendicular to the mountain range. So the Sierras run north-south, and the winds are very westerly. Provides very nice conditions for mountain wave. And a number of people took advantage of that. In the later years, Paul Bickle, who ran what was NASA Dryden, is now NASA Armstrong, was responsible for the X-15 project and all the things that led to NASA and to the early astronaut program. Paul was responsible for a lot of those early test programs that led up to space exploration. Sat back as the director, a person who, as an administrator, wasn't really supposed to do much in terms of quote-unquote aviation. And yet on the side, he was an avid pilot and sailplane pilot, glider pilot. And he took this all-metal, single-place glider to over 46,000 feet. Now, you have to keep in mind, at those altitudes, you have to have supplemental oxygen. That's taller than Mount Everest. That is very cold. It's every bit as harsh of an environment that you would expect for any other place on Earth. And he did it in an all-metal aircraft with a bottle of oxygen and a mask and some warm clothes. And then Bob Harris, 25 years later, beat his record again with another off-the-shelf glider. This is a Grobe 102 for any of those of you who are fancy keeping track of planes. It's, again, single-place composite aircraft made of fiberglass, and he got to just over 49,000 feet. At these altitudes, you're getting close to, you're beyond the death zone, as they would call on Mount Everest. You're getting very close to what's called the Armstrong line, which is about 63,000 feet. And at the Armstrong line, you need a pressure suit to maintain life, because if you don't have a pressure suit, the pressure of the atmosphere around you is low enough to cause your blood to boil, because the temperature of your body is at a point which is above the boiling point of water. It causes all kinds of problems, as you might imagine. So you can't go much higher than this without any kind of special equipment. So now I'm going to transition to the Perlin story. And it starts before I joined. I joined, as I said, about 9 years ago. It started with this gentleman, Einar Enevoldsen, who I greatly admire. Einar was one of those test pilots at Dryden at Edwards Air Force Base. He was a contemporary of Neil Armstrong. I was fortunate enough to meet Neil before he passed away because of Einar. Einar flew a chase plane on Neil Armstrong's X-15 rocket plane flights. He also is briefly quoted in the book The Right Stuff. He was one of those people that early NASA went to, and he said, "No, I don't want to be in a can. I want to fly an aircraft." Ainer had a very, very illustrious career, and eventually, back in the late 80s and early 90s, went to work for a company called Grobe, and that made that plane that I showed you in the last photograph, amongst other planes. He went to work for them in Germany, testing aircraft, and he saw this LiDAR image from Scandinavian Meteorological Society, and he realized that this was showing stratospheric lift, stratospheric wave lift. And he said, immediately had that aha moment that if that's stratospheric lift, you can fly a glider in that. And so he set about figuring out a way to do that. LiDAR, just to be brief, it's a type of measurement where you can bounce light off of particles and get information back. It's used in the self-driving cars these days. So before he tried to figure out, or as he was trying to figure out how to do this, he had to figure out what was causing it. And to make a much longer story short, it has to do with the polar vortex. Now, the polar vortex, a lot of people have heard about. It's been in the news and the weather. And it's to put it simply, it's a stratospheric cyclone that exists at the poles of our Earth when the Earth is in the winter months of that pole. So right now, we are coming out of winter here in the northern hemisphere. The polar vortex is stronger right now than it will be 6 months from now. As I said, it occurs at both poles, and it's intensified depending on the time of year. What happens is that pole of the Earth radiates heat to space because it's more shaded and it's not illuminated as brightly. That radiation, that loss of energy to space, helps to intensify the stratospheric winds around the pole and intensify that polar vortex. It does a lot of other things too. It tends to trap components in the atmosphere within the vortex, and that is one reason why there was an ozone hole a number of years ago, is because chlorofluorocarbons got concentrated in the southern hemisphere. And this is just a vector representation of the winds aloft, at the South Pole, and showing this. And then, just to give you yet one more graphic, this is a model, three-dimensional. Part of it will be three-dimensional model of the polar vortex over a past season, and then showing you the specific layers. It's mostly a stratospheric or upper atmosphere phenomenon, although it does influence the weather below us. And I won't go into the meteorology of why some of what goes on in the news about the polar vortex causing us so much concern and such is not necessarily true or always true. Suffice to say, it's an important feature that a lot of people don't know about and misinterpret, but we can utilize it to our advantage to fly to stratospheric levels in the atmosphere. Suspended in the upper atmosphere are what's called noctilucent clouds. It's very fine particulates of ice, fine crystals of ice and other chemicals that refract and reflect sunlight, and they're quite beautiful. And the reason I show it is not only are they visible at these extreme latitudes where we go, and are coincident with the environment to fly in, it also is where we get the name Perlin project, because in the Scandinavian languages, Perlin is the word for pearl, and of course this looks a lot like mother of pearl that you would find in a gem. So Ainer, putting all this together, realized yes, the conditions do look like they would be conducive for stratospheric wave flight. How am I going to get there? Now I got to build something. So he ended up partnering with Steve Fawcett, and Steve, who some of you may have heard of, was a commodities trader in Chicago, made a lot of money, and then decided he was going to set a lot of world records. Everything from high altitude ballooning with Richard Branson to sailboat excursions across the world to round the world flights to, before he died, rocket car. He was going to try to break the land speed record. So Steve was, and I didn't meet Steve, but I know a number of people now who are very close to Steve. Quite the character, very, very robust individual. So Steve decided he would step up. He thought this was a great record to break. He was in for the challenge. And so he and Einar, to make this a quicker story, because we only have so much time, borrowed 2 spacesuits from NASA, the spacesuit techs that go with them, and then upfitted a commercial off-the-shelf glider to be able to fly in this stratospheric lift. Our meteorologist, Elizabeth Austin, was trying to figure out the best place to go for the team. And initially, she said that they should go to New Zealand. Now, as I said before, the best features are ones where the mountain range is perpendicular to the winds aloft. And it just so happens you have to have the winds aloft increasing in velocity with altitude. They went to New Zealand for a couple seasons, but what they found was it really wasn't conducive because, as you see, and you can see down here too, New Zealand kind of sits at an angle, and the mountain ranges are actually in line with the angle of the islands, and so they're really a little bit off angle for the winds, which are going to go perpendicular to the mountains. They don't really cross them perpendicularly. You really want them to be going this way. But the winds don't go that way. They go from the west. If you track the lines, you'll see that. So they regrouped, and in season 3, they decided, well, how about the Andes? Sounds good. The Andes, long stretch of mountains, much more perpendicular to the westerly winds, and also far enough south. We can go far enough south to be coincident with that polar vortex. So we chose, or they chose at the time, again, this is the early 2000s, to go to El Calafate, which, I have a better slide a little bit later, it's pretty much southern Patagonia. It's as far south as really, it's not as far south as you can go, but it's pretty much where you go if you want to go to southern Patagonia. And in 2006, that glider that I showed you, Steve and Einar were able to go to just above 51,000 feet. This is the record trace, a little bit hard to see. This is a cross-section of the Andes Mountains. The red is lift, it's air going up. The yellow and blue is air going down. And you can see that there's a primary wave, a secondary wave, a tertiary wave. These things come in a standing pattern. And the green trace is where they got off tow, worked their way up, jumped back to the secondary, and kept going up. Now, their spacesuits inflated. They decided they didn't want to risk flying any further. They broke the record. They decided they would come down and they would build a new glider to go further. And that's where, and then just to say, this glider is now on display at the Seattle Museum of Flight, where it is available to the world to see. So I came in 2009. We had, just a design on paper. Unfortunately, Steve had died a year and a half before I came on board. So the money was gone. So we had a concept. We had a very small team. I was coming in focused mostly on the science mission and some of the technological instrumentation that was going to be necessary. And really all we had at the time was a plan. We had this plan to build this aircraft, and we had a design. And we had a few $100,000 in the bank. Now, again, anyone who's familiar with anything in aerospace, you don't think, oh, I can build a spaceship for $100,000. Well, that's true. You can't build a spaceship for $100,000, but as I'll tell you, you can build it for a lot less than you think. Through donations at first, we were able to get funds to start the process of building an aircraft. And again, this started about 2009, right when I came on board. We had secured some new funds, we had the design, and we were starting some tooling. I will say at this time, I guess with a little bit of money in the bank, we were able to recruit Dennis Tito, and anyone who maybe follows space, new space, Dennis was the first commercial astronaut on the International Space Station. He has a background in aerospace. He actually worked at JPL right out of college. He's an engineer by training, but he went into finance, and like Steve Fawcett, made a lot of money designing financial programs, and turned that money towards his first passion, which was aerospace. So he came on board about the time I started and donated some money to allow us to start fabricating. And so now I'm going to transition quickly to how an aircraft gets built. I'm going to go through these a little quickly, but suffice it to say, an aircraft or any complicated composite structure has to go through several phases. And we like to say you build the aircraft 4 times. The first time is just cutting out foam to make an initial mold. And it's not a mold that will be used for final production. It's just a mold to get the right shape. And from that, you make the negative of the mold that you will use to make the final shape. So you use composite materials, cover that, make the initial molding, the negative, and it comes in all sizes and flavors. All right, you see the boom, tail, the rudder, empennage, and then from that you make the positive molding to actually make the final parts. The wingspan of the aircraft is 84 feet, which is not the largest wingspan by any stretch of the imagination, even for a glider, even for a commercial glider. There's some that come close. But this is a very unique wing in that every section along the length has a different contour, which gives it efficiency in the realm of 60 to 90,000 feet. So this flies okay at low altitudes, but really has been designed to fly at extremely high altitudes. That's Dennis back here with part of the aircraft constructed. And then eventually we got to a test article. Now, so 3 years later, after all that work, we got to an initial test article. But it's not ready to fly. It's just a ship that is ready to be destroyed. And this particular one, we did a stress test where we sealed up the windows, which are those openings, holes on the front, and then filled it with water until it ruptured. So see where it fails and at what pressures it and which extremes it fails at. Likewise, with the wings, we have to go through a loading test. And this is very much what goes on at Boeing and Airbus. They'll take the actual wing of an aircraft and they'll place large amounts of sand or cement, and they will bend it under to a specific loading, and they will see if there are any deformities, cracks, stresses, and they inspect it in that configuration. And we did the same thing with our wing. From there, the aircraft goes to ground vibration testing, which gets into the world of flight dynamics, because ultimately we use this model to understand how the aircraft will fly at different altitudes. There's a thing called flutter that can happen with aircraft, where you get a resonant, you achieve a resonant frequency in the structure in flight, and that can literally shake apart a structure in an aircraft within moments if it's not corrected. So by doing ground vibration testing, we get a baseline model of how the aircraft will vibrate and in vibrating in flight. And then from there, we can do further testing in the air. It's not just build it and jump to 75,000 feet. Ultimately, now this was 3 years ago, we were able to finish. Along the way, as I said, most of that time we had money from small donations, a few donors on our project, members. We knew before we could do all this finalization, we were going to need a much larger chunk of money. We were able to go fundraising and caught the eye of Airbus, who spent about 6 months reviewing all of that work I just showed you. Not all of it, but they reviewed a lot of the work I showed you. And they came back at the end of that 6 months, and they sat down with us and they said, this is probably one of the best projects, most complete projects we've ever seen, inside or outside of our company. That you have done a fantastic job thinking through all the problems, and we are absolutely stunned that you were able to do it on the amount of money that you've spent so far. Yeah, we want to be your key donor going forward through the aircraft completion and test flights. So Airbus came on board. That's why it's called the Airbus Perlin Project 2. I'm going to skim through these pretty quickly because I know we're coming up on end of time. So just to say, there's a lot more that goes into it. The airframe is just the start. We have the environmental control systems. The pilots who fly the aircraft they actually live on a rebreather. So they breathe pure oxygen through a rebreather apparatus that scrubs the carbon dioxide out. If you're a scuba diver, there are rebreathers out there that do the same thing. This one actually was originally designed for miners, but we adapted it for our purposes inside the pressure cabin of the aircraft. The inside of the aircraft is actually pressurized just with air. So we maintain a positive pressure inside that pressure cabin so that there are no spacesuits. It's a shirt environment, short sleeve shirt environment. Well, not really, because it's pretty cold. So, you wear a flight suit with some heaters. But the cabin's pressurized to about 14,000 feet. We vary that depending on what we're trying to accomplish. And that differential holds the hatches shut and maintains the environment for the pilots. This is just a schematic of that rebreather system. There are a lot of electronics to go in, monitor the CO2 levels, oxygen levels, and the pilots themselves for their pulse ox. This is a view out of the front seat of the aircraft. Some standard instrumentation that you would find in any aircraft. That's an EFIS, or an electronic flight information system, which has all kinds of information on it. This is a subsystem we specifically designed and programmed amongst us that monitors a whole bunch of things, not just what's on that screen. Picture from the rear seat. So the rear seat is not a passenger. A lot of people have come forward and said, well, I'll give you X amount of money if you give me a ride. Unfortunately, the rear seat pilot's job is to keep the front seat pilot alive. And it's a very sophisticated back seat because you're responsible for all that life support that I just described. We have a telemetry system. I actually designed all of this. I'm an amateur radio operator, so we use amateur radio to to send data from the aircraft to the ground. And so we have a display of all of those systems that you saw inside the aircraft. We get a duplicate, and this is hard to see in this light, but we have a whole screen of all the data that they see, we see. And it's beamed to the ground through a telemetry system. In addition, we obviously can talk to the pilots and keep in radio communication. In addition to the aircraft, we built a simulator. So knowing that eventually we'll need to train more pilots, there are only 4 people qualified to fly it right now. I am not one at the moment, but I'm on the list for the next round. We have the simulator, and the simulator is a full mock-up, has all the same instrumentation as the real aircraft. It projects when this is going, it projects a simulation of the surroundings, and you can fly the aircraft and test out emergency procedures. We have an active STEM program. We've worked with Teachers in Space, which is based out in New York, but that reaches out to schools across the country and even internationally. I think we have at least one school in Canada. We, about a year and a half ago, put out a proposal, or call for proposals, to schools across the country with Teachers in Space to design CubeSat experiments. We got 24 schools to participate across the U.S. and one in Canada. From those, we selected 12 to build experiments, and those 12 experiments have flown now on a number of flights. We have a payload bay behind the pressure bulkhead, and that payload bay can access the atmosphere from the outside of the aircraft and can also tie into some of the other aircraft instrumentation. So 2 years ago, we made our first attempt in Argentina with the Perlin 2. We're still in a test flight mode. We can't just go to 90,000, 100,000 feet. We're building our way up in 5,000-foot increments, testing the flutter, that vibration sensitivity of the aircraft, testing how it flies, testing where it stalls, where it's not flying. But we were confident we were ready to go to Argentina to start working our way up to set ever-increasing records. In the first season, we were not able to get much above 25,000 feet. Very disappointing, actually. We got there late in the season, though. Their winter is our summer, so the best wave season is from July through the beginning of September. We got there late. We got there really kind of towards the end of August, or middle of August, the first season. But last year, we got there earlier. We started about mid-July. I was actually in El Calafate for 6 weeks, 5.5 weeks. And we based our Campaign 2 at the El Calafate airport. This is the hangar on the edge of the airport. We utilize it for all our operations and maintenance. This is what a good southern Patagonian sky looks like. And fortunately, after many weeks, we were getting to 35,000 feet routinely. But what happens is the conditions have to be just about right, because what happens is that lower wave activity gets interrupted by the tropopause, that area of the atmosphere between the troposphere and the stratosphere. And it's only on certain days where they bridge. And on the day, literally the day after my 50th birthday, September 3rd of 2017, we had a record day. I was in the tower, and we got to about 30, it was actually closer to 40,000 feet. And they made the jump back and this is what we see routinely, that there's a very strong primary wave, but then the intensities in the secondary and tertiary waves at those higher altitudes. They had jumped back to the secondary wave and were able to get in to sustained lift above 40,000 feet. At 40,000 feet, the lift was only getting stronger, and we have we have the ability to monitor this. So I was able to monitor this on my phone using an app we built, and actually an app that anyone can look at when we're in season next year or this year. But we were able to get to 52,221 feet. That's what the sky looks like at over 50,000 feet in a glider. We could have kept going higher. The lift, we stopped at that red line. Actually, we've amended this now based on the FAI, which is the international body which awards these things and justifies them, has now clarified we actually have 52,221 feet. But you can see that the lift was getting stronger with altitude. We had no doubt we could have easily gone to 70,000 feet. But we had set a limit because of our flight testing and the battery of the aircraft not to go any higher, and we stopped at that altitude knowing that we had broken the record. And this is what a party looks like in the middle of nowhere when you've set a world record. So with that, we are now back in the States. The aircraft's back, and we were just notified about 2 weeks ago that we are up for the Collier Trophy. Now, the Collier Trophy is probably the longest standing award in aviation in America. To give you some idea of the awardees in the past, the crew of Apollo 11 was an awardee. SpaceX has been an awardee. The who's who of all the major milestones in aviation since the Wright brothers have won a Collier Trophy, and so we were nominated. We are nominated for the Collier Trophy. Now we'll know in March if we win it. Although, as you look there, you'll see one group that I'm actually really happy for them. They've done a fantastic job, and that's the Cassini project team. It's hard to go up against one of the most successful space missions of all time at Saturn with the Cassini project team. But we are very proud of being nominated. It is the Academy Awards of Aviation. And then more to come. So the aircraft is back in Minden, Nevada now, or it's been back in the States for several months. We're modifying it, changing it, putting in a new battery, doing all kinds of things. I'll be out there in April to do some work. I'll spend a couple weeks. And then by the end of May, we will box it back up, and it'll be on a slow boat back to Argentina, Patagonia, where we will attempt to go. Our goal this season is 75,000 feet, which, again, is as exciting and challenging as you might think. It is not something that's easy to do, and we've done it on a budget that's at least 2 orders of magnitude less. And I'm not at liberty to say the exact amount, but you'd be surprised how little we've spent. And it's mostly because of the passion of a dedicated group of individuals getting together and saying, I'm going to do this, and we're going to keep going until we do this. And we finally did it. So with that, I'll entertain it. I know we don't have a lot of time, but I'll entertain any questions and thank the sponsors that have helped us out over the years.
Do we have any questions?
Do you fly it, or do you have a jockey that flies it?
Do I fly
it, or do you have a jockey that flies it?
Well, so the question was, do I fly or do I have a jockey that flies it? So the team has 4 qualified pilots. Of course, I am a pilot. But right now we're in a test flight phase. So 2 of our qualified pilots who are flying right now are bona fide 110% test pilots. They've flew for the military, and their job has been to analyze the flight of new aircraft. And then the other 2 people One, Morgan Sandercock is lead engineer. He's actually built a lot of the systems with the rest of us, but I mean, he's taken the lead on several of the critical systems. And then the third person is a highly seasoned glider pilot that's been flying in Wave for decades. So as we get through the flight testing phase, there will be opportunities for other members to qualify and to fly. But like anything, it will take working in the simulator, doing flights with the people who are already pre-qualified. It's not an easy aircraft to fly. There are easy, and I've flown now a lot of different aircraft. Each one is different, and everyone has its unique idiosyncrasies. This one is pretty heavy at lower altitudes, but actually gets easier to fly as you get higher. So I hope to. I'm not writing it off my list, but it's going to take some work, and it'll probably be at least another season or so. Let's hope that there will be some opportunities before Smithsonian calls, because I didn't mention that, but that's also kind of already in the works. That we've been, it's been hinted. Would this go in the Smithsonian? Would you like this to go in the Smithsonian? And of course we will. So it's a race. It's a race to get in, get trained, and fly before it ends up in the Smithsonian Museum. Yep.
Sorry if you actually covered this, but so how do you? I had kind of three questions. What do you use for like the initial velocity to get started, and is it the lift of the standing waves that help fight off any drag effects? And then my final question is, like, if you want to stop and come down, what do you do?
Right. No, all good questions. So the initial velocity getting going is with a tow plane. So like any other glider, it's not a motor glider. We use a tow plane. We use a motorized plane and a giant rope. And we attach the rope to the tow plane and to the glider. And the two take off together in tandem. And the purling glider is towed up to about anywhere between 8,000 and 10,000 feet, depending on where the lift is that day, and then they get off. So there's a release mechanism which lets the rope go from the glider, and the tow plane carries it back to the airport. Glider gets off and then looks for that lift in the atmosphere. So you're right. There is the four forces at play. Gravity pulls against the lift, and the drag against the forward momentum. But what happens in wave is that standing wave is like an elevator. The atmosphere is going up that peak, and if you're in it, all that air is going straight up. So there's enough lift to overcome the drag and the gravity to lift the aircraft. And what you do is you match your airspeed to the wind speed, the forward wind speed. And the aircraft literally parks in the atmosphere and just goes up like an elevator. Now, I've flown this. We have wave around here. We have it at Mount Mitchell. I've flown in Mount Mitchell wave several times. I've been to over 20,000 feet in the wave here. And it's the freakiest thing in flying because it looks like the aircraft has stopped. And you can tell this if there are other aircraft in the air with you. You look out the cockpit and you see that those aircraft are just stationary below you, and relatively speaking, they don't get bigger because you're both going up, or you're all going up. But you look at the altimeter and it's winding up. You're going up and up and up, and everything you see is you're not moving. So it is a very unique experience to fly in, and then to come back down, we have spoilers or air brakes on the wings. And it's a device a mechanism where you pull a handle and metal slats come out of the wing and disrupt the lift over the airfoil. And that disrupts the lift enough to then allow you to come down. You basically create more drag and less lift, and that allows you then to descend as opposed to going up. And you can control going up and down by how much you put that out, or if you put it out at all. No, the Armstrong line is about 63,000 feet. Well, because we have a pressure cabin that, if I go back and just take. Well, and actually, the aircraft leaks on design. I won't go back to the picture, but so yeah, so the pilots breathe from a mask, the pure oxygen in the rebreather, and then the cabin itself is pressurized with air to about 14,000. You would experience at about 14,000 feet, and that keeps the differential between the outside and the inside big enough to keep the seals intact and to keep pressure on the inside of the cabin. So we effectively have an inside pressure of about 14,000 feet. And of course, if you've gone skiing in Colorado, you know what it's like at 14,000 feet. So that's how our blood doesn't boil. We have enough pressure around the pilots to keep them safe. In addition, the cabin's has some other environmental controls to pull out moisture and to do some things to keep the pilots comfortable. But it's that pressure difference that would cause the pilot to have a major problem, much like the bends. It's like if you have any concept or you've been scuba diving, if you come up too fast and the nitrogen comes out of your blood and it bubbles, right? Because you're going from increased pressure to less pressure rather quickly, and all that wants to come out of your system. It's a similar kind of thing. It's why we breathe pure oxygen. We're trying to get that nitrogen out of our system, but it's the pressure around them that keeps their blood from wanting to boil.
Are you in any danger of getting high enough so that the lift mechanisms won't, like your lift mechanisms won't work?
No, at 90, 100,000 feet, we're above 97% of the atmosphere, but 3% of atmosphere is still enough for the wing to fly. It just means you have to go, your ground speed is really high. So at 90,000 feet, our indicated airspeed, so what the gauge in the aircraft would say we're flying at, is about 55 miles an hour, 53 miles an hour. But our true airspeed and relative to the ground is like Mach 0.6. So, and that's because the air density is so low, the gauge registers, low, but we're so high that we have to fly that fast to maintain the lift over the wing. It sounds kind of crazy, and it is. I mean, it's not supersonic, but Mach 0.6 is pretty fast.
That's one more question.
Mm-hmm.
Different topic. You're talking about resonant frequency. Do you intentionally tune the resonant frequency, like when you're designing a building? Are you aiming for a specific frequency?
That's a great question. No, yes and no. There are norms in building an aircraft where you stay away from certain kinds of designs. Unfortunately, it's such a complicated thing when it all comes together. The resonant signature is what it is when it's all said and done. You do steer away from certain designs and you maintain certain principles to get the best possible outcome. But at the end of the day, you got to test it. What's that? Yeah. Well, and that's why we take the flight test. That's why you have to go through a flight test regime where you do these tests every 5,000 feet. So in the wings, we have mechanisms that vibrate the wings, and they can do it symmetrically or they can do it asymmetrically. And we intentionally vibrate the wings as we increase in altitude to vibrate them and then sense, is there any abnormal resonance going on? And we can we basically quantify that, and we can say, okay, we're safe to go to the next altitude, or we're not. We got to think about what's going on here. So far, everything we've done with our testing has demonstrated we're cleared to go. We're now clear. We have cleared ourselves based on the data to go to 65, 70,000 feet, not be concerned. The higher we go, the more we don't know, and of course we got to continue to do that testing.
So,
Just out of curiosity, what ballpark are these frequencies? I used to be an audio engineer, which is why that.
Oh, they're well, they vary. They're generally pretty low frequencies. These are in the 10 hertz all the way up to, I want to say we have 1,000 hertz in there. Yeah. Yep. Yeah, but we do some really low frequency. I mean, it spans quite a spectrum.
Michael, I don't know if you can hear me.
Yeah, I can hear you.
Okay. Great lecture.
Thank you.
We're going to thank you officially in a second. But, there's a lot of students here, and there's a lot of different folks representing different sciences. Is there any possibility that a student could engineer a project that you could take down to Argentina with you from SciTech?
Mm-hmm. Yeah, there's certainly an opportunity to build experiments for our CubeSat payload bay. We just have spent 2 months rebuilding the payload bay, re-engineering it, rebuilding it. And I just worked with he used to be our engineer intern. He's now just graduated with his degree in engineering, mechanical engineering. So, but he and I have just redone our experiment specification, which if anyone is interested, we can provide. And it outlines the physical and electrical requirements, the basic requirements that an experiment has to fulfill to be able to fly in our payload bay. It's not terribly difficult. I'd be happy to talk with anyone, provide that to them and talk with anyone about what they would like to do. I'm actually building one myself.
That's great. Any other questions? Yeah, Scott.
Mike, I just got a question. What's been the interaction between you and NASA? You mentioned with the atmosphere, the stratosphere, it's similar to the Martian atmosphere.
Surprisingly, I mean, over the years, NASA's been helpful. Like with the spacesuits, they didn't have to loan them to Ainer and Steve, but Ainer is so well known that they did. With regards to funding and other data, no funding from NASA. They have provided us with some data and expertise at certain points in time. We continue to keep in contact with them. There are opportunities for them to do some follow-on experiments while we're there so that we have a more complete data set. They have some aircraft and some other instrumentation which would be useful to fly alongside of us. Not at our altitudes, but specifically LiDAR, which is a type of instrumentation, again, get particle data and measurements from what's in the atmosphere. And that can look up, and so that would be valuable. They've talked about sending aircraft down. So there have been those kinds of things, but it's not been super close. Well, thank you, everyone, for your attention.
Yeah.
I know it was slightly long, but hopefully you enjoyed it.
Thank you, Michael.